Take a look at this image from the James Webb Space Telescope. At first glance, it looks like a beautiful planetary nebula, something similar to the famous Eye Nebula. These types of nebulae are the final evolutionary stage of medium-mass stars, like our Sun, which, after going through their red giant phase, aren't massive enough to explode as supernovae. Instead, they simply shed their outer layers into space, forming a bright bubble of glowing gas. At the center of such beauty, there's usually a former stellar core, a white dwarf, slowly cooling down. But in this image, we're looking at something very different. The central star of this nebula is not a white dwarf. On the contrary, it's an actual stellar giant with a mass around 30 times that of the Sun, and it's still actively blasting material into the surrounding space. WR-124 has already thrown out about 10 solar masses into the cosmos. Just imagine that. It's literally tearing off chunks of its own hot plasma, and it won't stop until it finally explodes in one of the most powerful outbursts in the universe. This is what Wolf-Rayet stars do, a very special and incredibly rare class of stars. On average, you'd find just one of them among 100 million others in our galaxy. Not only are they massive and huge, but they're also unbelievably bright, often millions of times more luminous than the Sun. And despite their rarity, they play a crucial role in shaping the flow of matter throughout the galaxy. So let's take a closer look at the most extreme type of stars. Mid-19th century, two astronomers, Charles Wolf and Wolf-Rayet, are studying stellar spectra using a 40-centimeter telescope at the Paris Observatory. This was a new era in astronomy, when scientists began breaking down starlight into its components to identify the chemical makeup of celestial objects. Usually, stellar spectra showed familiar patterns. Some wavelengths of light were simply missing. These dark gaps were absorption lines, signs that the star's outer layers contained various chemical elements capable of absorbing specific parts of its light. That's what Wolf and Rayet were used to seeing when observing the spectra of stars. But then, in the constellation Cygnus, they stumbled upon three stars that looked completely different. Instead of missing lines where atoms were absorbing light, they saw extra bright lines, emission lines. Clearly, these were very unusual stars, the astronomers thought, but they couldn't explain them at the time. And for decades, astronomers scratched their heads, trying to understand what exactly they were looking at. In the early 20th century, Edward Charles Pickering suggested that at least some of the Wolf-Rayet stars might actually be the central stars of planetary nebulae, which share similar spectral features. And in a way, he was right. Let's start with the basics. Emission lines appear in a spectrum, unsurprisingly, due to emission. The culprits here are atoms of various chemical elements. They absorb high-energy photons and then re-emit them. When atoms absorb photons of a specific wavelength, they jump to a higher energy level, but they can't stay in that excited state for long. After just a few microseconds, or even nanoseconds, they drop back down to their lowest, or ground, energy level. And this transition releases energy in the form of a photon with a specific wavelength. These are exactly the photons astronomers detect as emission lines in a spectrum. And by the way, emission lines are typically very narrow by nature. I mean extremely narrow, about 0.01 nanometers wide. But in the spectra of Wolf-Rayet stars, it's the opposite. The lines are broad, very broad. There are a few reasons why this happens. Some are purely quantum mechanical because of the fundamental uncertainty in the properties of particles, but others are due to motion. Imagine that the atoms emitting the photons are moving at different speeds relative to you and your telescope. Because of the Doppler effect, the photons will reach you with different frequencies. For example, think of an accretion disk around a black hole. On one side, matter is moving toward you. On the other, it's moving away. Atoms moving in your direction will have their light shifted toward the blue, meaning a shorter wavelength. Atoms moving away from you will be redshifted. Their wavelengths get longer. So, in total, the photons from a single source arrive with a range of energies, or wavelengths. In the spectrum, you won't see a narrow, sharp line. You'll see a broad one that stretches across a wider range of wavelengths. In the first half of the 20th century, astronomers finally understood this principle, and it revealed the true nature of Wolf-Rayet stars. Scientists realized that the material emitting the photons is being blown away from the star in all directions, and at extremely high speeds. we're talking hundreds, even thousands of kilometers per second. That's already a few percent of the speed of light. So, what kinds of stars are capable of producing something like this? To understand that, we need to look at a famous tool in astronomy, the Hertzsprung-Russell diagram. It shows different types of stars based on their temperature and color. The most prominent and longest band on this diagram is called the main sequence. Just a reminder, this is the phase in a star's life when it still has enough hydrogen to sustain nuclear fusion. It's kind of like the star's adulthood, when it shines steadily, maintaining balance. Down in the lower right of the main sequence, we find cool and dim red dwarfs. But as we move higher and to the left, we see stars that become progressively hotter and more luminous. Skipping past our sun, you'll notice stars turning whiter and even bluish as their temperatures rise. And finally, all the way at the top left, right at the edge of what stars are capable of, we find them, the hottest and brightest stars. These are the O-type stars, blue-white giants with typical masses between 15 and 80 times that of the Sun, and surface temperatures exceeding 30,000 Kelvin. Compare that to the Sun, whose surface sits at around 5,500 Kelvin. At the same time, these stars are extremely massive, and on the main sequence, the rule is simple. The more massive a star is, the hotter and brighter it becomes. But that comes at a cost. O-type stars live very short lives, typically no more than 10 million years, so we usually see them only near the regions where they were born. In fact, their intense blue-white glow is what lights up the spiral arms of galaxies. Still, despite their brightness and prominence, O-type stars are very rare. Physics makes it hard for a gas cloud to collapse into a single star that's 30 times the mass of the Sun. It's much easier for it to break into pieces and form many smaller stars instead. And if you add their short lifespans to the equation, it becomes clear why there are only a few tens of thousands of them in our entire galaxy, among over 100 billion other stars. But Wolf-Rayet stars are even rarer, because they represent just one possible evolutionary path that some of these blue-white giants might follow. Imagine a star with more than 25 solar masses, still in its main sequence phase. As we've said, it's incredibly hot, tens of thousands of Kelvin, and that heat creates powerful stellar winds. Yes, even while peacefully burning hydrogen, such stars lose vast amounts of material. These stellar winds can strip away up to 2 Earth masses of material every single year. Just to put that in perspective, our own Sun can blow off the equivalent of 1 Earth mass, but it takes about 45 million years to do it. The hotter the star, the more it loses. Why? Because hotter stars emit higher energy photons. When these photons are absorbed by free ions in the star's outer layers, they transfer more momentum. To put it simply, high-energy photons crash into free ions, get absorbed, and the momentum they carry gives those ions a push upward. In other words, radiation creates pressure, enough pressure to literally push matter out into space. That's what we call a stellar wind. But the real storm begins in the final stages of a blue-white giant's life. Once a star leaves the main sequence, it starts burning the remaining hydrogen in its core. At this point, it can no longer maintain the stable balance of pressure, gas, and radiation pushing outward against its own gravity. Gravity begins to win. As it takes over, the star starts to collapse in on itself. And as we know, compression leads to heating, so the core gets even hotter, igniting helium fusion. Meanwhile, the outer layers begin to puff out and drift away, exposing hotter inner regions. That means the surface temperature skyrockets, reaching 90,000 Kelvin or even more. And as we've seen, higher temperatures mean more powerful radiation, so the stellar winds intensify, blasting outward at incredible speeds, 2,000, even 3,000 kilometers per second. This is when the star becomes a Wolf-Rayet. Now the radiation pressure becomes absolutely terrifying, 3 to 4 times stronger than the winds of its O-type predecessor. In astrophysics, there's actually a known upper limit for how bright a star can get before radiation simply tears it apart. This is called the Eddington limit. And Wolf-Rayet stars? They're brushing right up against it. Their blinding brilliance is so extreme, it causes their surface layers to literally peel away, blown off by this relentless, superheated light. It's hard to even imagine such intensity. People sometimes call it a solar hurricane, but really, that doesn't even come close. Picture the gentlest breeze on a calm day, and now compare that to a jet of water from a fire hose. That's the kind of difference we're talking about. Wolf-Rayet winds are 10,000 times stronger than the sun's. Naturally, the loss of mass is enormous. In just 100,000 years, even one of the less massive Wolf-Rayet stars can shed an amount of mass equal to the entire sun. And 100,000 years, by cosmic standards, is basically nothing, just a blink. Astronomers estimate that during this brief stage, lasting just a few 100,000 years, a Wolf-Rayet star can lose 50 to 90% of its original mass. That means an O-type star that started with 30 solar masses might finish this phase weighing just 10 to 15. Imagine how much matter is being hurled into space. Of course, keeping up such extreme temperatures and luminosities burns through the star's nuclear fuel at an insane rate. This phase doesn't just mark the beginning of the end, it accelerates it. Stars with up to 100 solar masses usually end their lives in a spectacular supernova, often a type IB or IC. Some are even expected to explode as hypernovae. Think of a regular supernova on steroids. And the most massive ones, those with between 130 and 250 times the mass of the sun, might go out in a rare kind of explosion called a pair instability supernova. It's a special kind of cataclysm that completely obliterates the star, leaving behind nothing. No neutron star, no black hole, just a titanic flash, and then silence. Interestingly, the spectra of Wolf-Rayet stars puzzled astronomers of the past, not just because of their broad emission lines, but because they showed almost no hydrogen, which, as you might imagine, is not exactly what you'd expect from what are essentially giant molten balls of hydrogen and helium. But here's the thing, Wolf-Rayet stars are stripped stars. They blow away their hydrogen envelopes, exposing their hot, inner layers rich in helium. In a way, we're looking directly at the stellar core, one that, in addition to helium, also contains carbon and other heavy elements the star managed to forge during its short, fiery life. So naturally, we classify these stars based on their chemical fingerprint. If their spectra are dominated by ionized helium and nitrogen, they're labeled WN. Others, where ionized helium, carbon, and oxygen take center stage, are known as WC stars. In rare cases, oxygen even overshadows carbon. Those are called WO stars. No matter the type, the presence of these heavy elements in the spectrum is a sure sign that the star is racing toward its brilliant end. But before they die, Wolf-Rayet stars can trigger some truly special cosmic events. These aren't just spectacular to look at, they also play a key role in the ecology of their galaxy. For one, their fierce winds inject energy into the interstellar medium, compressing nearby gas. And as you might recall, that's exactly the kind of push that can trigger new star formation. In some cases, these winds carve out beautiful spherical nebulae, glowing cosmic bubbles like WR31A. This particular nebula is about 20,000 years old and is still expanding at around 60 kilometers per second. But perhaps the most important gift these stars offer their galaxies is dust. Because once the hydrogen envelope is gone, the star doesn't stop shedding material. It continues blasting heavy elements into space. And those elements, they condense into tiny grains of dust. Dust plays a vital role in the galactic cycle of matter. It absorbs and scatters harmful ultraviolet radiation, shielding fragile clouds of molecular hydrogen from destruction. It also helps those clouds cool more efficiently, absorbing energy from atomic and molecular collisions and radiating it away as infrared light. And cooling is critical. Without it, gas clouds can't collapse into protostars. So dust isn't just helpful, it's essential for star formation. And that's not even the end of it. Dust is where planets are born, where organic molecules can form. It's where, quite literally, we come from. We are made of stardust, and in large part, it's thanks to stars like the Wolf-Rayet. Astrophysics has always had a bit of a problem explaining just how much dust there is in galaxies, including our own. There's simply too much of it. One of the likely sources scientists now believe may actually be Wolf-Rayet stars. These stars might account for a significant portion of the Milky Way's dust budget. Take, for example, this stunning system called WR140. At its heart lies a Wolf-Rayet star, surrounded by layers of interstellar dust, beautifully captured by the James Webb Space Telescope. At first glance, those rings might look like some kind of image artifact, but trust me, this is a real natural phenomenon shaped by dust. What's even stranger, though, is the very presence of dust so close to such a hostile star. In astrophysics, dust is a bit like snow. It thrives in calm, cool environments. Not exactly what you'd expect near a blazing hot, aggressive object like a Wolf-Rayet star. Even if such a star is ejecting carbon, oxygen, or nitrogen into space, the surrounding region is usually too hot for any of that material to condense into dust. So how is it possible that dust not only forms but does so in such striking patterns? The answer lies in the fact that WR140 isn't a single star, it's a binary system. Alongside the Wolf-Rayet star orbits another massive blue giant, this one of spectral type O. Back in the 1980s, astronomers noticed that the dust rings seemed to match the orbital period of the pair, about 8 years. That led scientists to suspect that the dust forms during the closest approaches between the two stars. As you might recall, even on the main sequence, blue giants produce powerful stellar winds. So when the two stars draw near, their winds collide, slamming into each other, slowing down, and cooling off. Under these conditions, dust and gas can finally begin to condense. And with each close pass, a new shell of dust forms, wrapping around the stars like the layers of an onion. There are other fascinating shapes that dust can take. For instance, the binary, or potentially even triple system WR104 forms a perfect spiral. The two main stars, one a Wolf-Rayet and the other a blue-white giant of spectral class OB, orbit just 2 astronomical units apart. To put that in perspective, that's about the distance from the Sun to the asteroid belt. Because of this close separation, it takes the pair only 241.5 Earth days, roughly 8 months, to complete one orbit around their shared center of mass. That means astronomers can study the dynamics of the system almost in real time. The spiral dust tail is likely created by the same process as the shells of WR140, through the interaction of stellar winds. As the system rotates, the dust is carried outward, forming a continuous spiral. Similar spiral tails have been observed in other Wolf-Rayet systems as well, leading astronomers to classify them into a separate group known as pinwheels. By the way, WR104 briefly rose to fame in 2008. Scientists studying its physical properties happened to mention its potential danger to Earth. At the time, people had few legitimate reasons to worry about the end of the world, so they were eager to invent new ones, like the infamous Mayan 2012 predictions. So when the researchers wrote in their paper about the non-zero chance of a gamma-ray burst from this system, it set the internet on fire. Now it is true that massive stars can be candidates for gamma-ray bursts, but not all of them. This scenario is usually expected only from rapidly rotating stars. During core collapse, when a black hole forms, rapid rotation allows an accretion disk to form around it before the entire star falls in. That disk is what enables 2 focused jets of matter to blast out along the black hole's poles. These jets carve their way through the collapsing star and burst into space as a powerful pulse of gamma radiation. Stars that rotate more slowly might not form such a disk, and instead simply explode as supernova, with no gamma-ray burst phase at all. As it turns out, the 2 stars in WR104 might be rotating fast enough. No one knows for sure. But models of the dust spiral and their possible interactions hint that this could be the case. What's more, earlier observations suggested that the system's rotational poles may be aimed almost directly at us, and the system lies just 8,400 light-years away, which is relatively close in galactic terms. That's why the authors very carefully suggested that a gamma-ray burst from WR104 could pose a danger to Earth. However, despite the buzz, there's no real reason to worry. First, there's only a very small chance that either the Wolf-Rayet star or its companion will go through a gamma-ray burst phase before exploding as a supernova. These events are usually seen in low metallicity galaxies, which the Milky Way is not. Of course, that doesn't completely rule out the danger from a supernova either, since much of the energy from that explosion is also channeled along the star's poles. But later research showed that the star's rotational axes are likely tilted relative to the dust spiral's plane by about 30 to 40 degrees. So if a gamma-ray burst or supernova does occur in WR104, it's unlikely to hit us directly. Everyone worried about this can breathe easy, except perhaps astrophysicists, who now have to figure out why the stars and the dust spiral don't seem to be aligned in the same plane. Overall, Wolf-Rayet stars still hold many mysteries. For example, astronomers still don't fully understand their internal structure or how it changes over the course of their evolution. The role of magnetic fields in all these violent processes is also unclear, and measuring them is extremely difficult. The main problem is a lack of data, largely due to the rarity of these stars in our galaxy. To date, we know of only around 700 Wolf-Rayet stars in the Milky Way, and estimates suggest there may be no more than 1,000 in total. With lifespans of just 200,000 to 500,000 years, it's no surprise they're so scarce. In fact, only 2 of them can be seen with the naked eye, and both are southern sky treasures. The most famous and the brightest is Gamma Velorum, located in the constellation of the same name. It's one of the brightest stars in the southern hemisphere, though in reality it's a quadruple system, one component of which is a Wolf-Rayet star. However, most of the system's brightness comes from its companion, an O-class star. You've probably noticed that Wolf-Rayet stars are often found paired with blue-white giants. That's because they all tend to be born in dense stellar clusters and frequently form binary systems. Many other Wolf-Rayet candidates have been found outside our galaxy. There are even entire Wolf-Rayet galaxies, so rich in these stars that their spectral lines dominate the galaxy's overall light. Astronomers have discovered around 150 to 200 Wolf-Rayet stars in each of our major galactic neighbors, including Andromeda, the Triangulum Galaxy, and of course, the Large Magellanic Cloud. It's in the Large Magellanic Cloud, specifically in the Tarantula Nebula, the most active star-forming region in the local group, that the most massive and luminous known star resides, R13601. This colossal object is about 200 times more massive than the Sun, and over 6 million times more luminous. Yes, it's a Wolf-Rayet star, and every year it loses a mass equivalent to 22 Earths. In just 5 seconds, it emits as much energy as the Sun does in an entire year. Astronomers estimate that it may have started its life with a mass of around 300 solar masses. How such a monster could even form is still an open question. It's widely believed that stars don't typically form with masses exceeding 150 suns. That's due to the Eddington limit. Above that threshold, radiation pressure becomes so intense that it blows away the infouling material, preventing further growth. So, stars more massive than this are thought to result from the merger of 2 already massive stars, not from direct formation out of a gas cloud. Yes, stars can merge and become true cosmic giants. We've become used to thinking of stars like Betelgeuse as stellar titans because of their huge size. But while red supergiants are physically larger than blue-white giants, they typically have only around 10 times the Sun's mass. Their massive size comes from a bloated outer atmosphere and a cooler surface temperature, even cooler than our Sun's. In my opinion, the most massive Wolf-Rayet stars easily outclass them in every extreme. And that's what makes them among the most awe-inspiring objects in the universe. They also play a crucial role in galaxies, especially when it comes to triggering star formation. So studying them in more detail is a promising frontier in stellar astrophysics.